Good morning, students. I hope all you are safe. And in today's maths class, we are going to do the continuation of the yesterday's one, modulus of a complex number. Yesterday we learned the properties of modulus as well as we did few problems. Okay, just we can recall some of the properties. That is modulus Z. If Z is equal to x plus iy. If z equal to x plus iy, modulus z is equal to, we know that is root of x square plus y square. And moreover, modulus z is equal to modulus z bar. Then, if it is in multiplication and division, the modulus will be separated. Then modulus z1 plus z2, triangle inequality, isn't it? Always less than or equal to modulus z1 plus modulus z2. And we have learned that real part of z is less than or equal to modulus z. Imaginary part of z is also less than or equal to modulus z. Isn't it? Then, two important things, modulus of modulus z1 minus modulus z2 is less than or equal to modulus z1 plus z2, which will be less than or equal to modulus z1 plus modulus z2. The same way, modulus of modulus z1 minus modulus z2 is less than or equal to modulus z1 minus z2, which will be less than or equal to modulus z1 plus modulus z2. Using these two, we are going to do 2-3 problems. Now, shall we move to the problems? Example 2.13. If modulus z equal to 2, show that 3 less than or equal to modulus z plus 3 plus 4i less than or equal to z. Say, modulus z value is given. So, I am going to separate this into two parts. Let z1 equal to z and z2 is equal to 3 plus 4i. In between plus is there, isn't it? So, we can use this first condition. Then, and write, we know modulus of modulus z1 minus modulus z2 is less than or equal to modulus z1 plus z2 less than or equal to modulus z1 plus modulus z2. Now we can substitute and check it. Okay. See, modulus of modulus z minus z2, that is modulus 3 plus 4i less than or equal to, this is modulus z plus 3 plus 4i less than or equal to modulus z plus modulus 3 plus 4i. So, before that, in the side, if you want, we can find it out, modulus 3 plus 4i, which will equal to root of 3 square plus 4 square, isn't it? So, we may get root 9 plus 16, root 25, which is equal to 5. Or even you can write it modulus z2. Modulus z1, z value is 2 and this modulus z2 value we have got it as 5. Now we can substitute in this. This is modulus z2 minus this is 5 less than or equal to modulus z plus 3 plus 4i, which is less than or equal to modulus z2 plus 5. See, this is modulus minus 3 less than or equal to modulus z plus 3 plus 4i less than or equal to 7. Modulus of minus 3 means we know that is 3 less than or equal to modulus z plus 3 plus 4i, which is less than or equal to 7. This is one method to prove it. Or else first you have to find out this, keep it as equation number 1. Again we have to find out this one, equation number 2 from 1 and 2. Using that also you can prove this problem. Okay. Similar way, we will do two problems from exercise. Exercise 2.5, fourth problem. If modulus z equal to 3, show that 7 less than or equal to modulus z plus 6 minus 8i less than or equal to 13. So modulus z value we know. This we can separate. See, let z1 equal to z and z2 is equal to 6 minus 8i. Is that clear? Then find it out. The modulus z1 is modulus z which is equal to 3. It is given. Then modulus z2 means modulus 6 minus 8i, isn't it? That is root of 6 square plus minus 8 the whole square. 6 square 36 plus 8 square is equal to root 36 plus 64 is 100. We know 10 into 10 is 100. So our answer is 10. Here in between plus is there, isn't it? So I am going to use, see, we know or we have modulus z1 minus modulus z2 less than or equal to modulus z1 plus z2, which is less than or equal to modulus z1 plus modulus z2. Now we can substitute the values. See here modulus, this is modulus z minus modulus z2. The value is 10, or directly we can substitute z1. This is 3 minus 10 less than or equal to modulus z plus 6 minus 8i less than or equal to 3 plus modulus z2 is 10. See, this is 3 minus 10 is minus 7 less than or equal to z plus 6 minus 8i less than or equal to 30. Now modulus of minus 7 is plus 7 less than or equal to modulus 6 z plus 6 minus 8i less than or equal to 30. So if you know that this property, it will be easy for us to prove. Say, same way, problem number 5, if modulus z is equal to 1, show that modulus, 2 less than or equal to modulus z square minus 3 less than or equal to 4. Question number 5, if modulus z equal to 1, show that 2 less than or equal to modulus z square minus 3 less than or equal to 4. So here z square minus 3 is there. So I am going to take, let z1 is equal to z square and z2 is equal to 3. Okay. Now modulus z1 is modulus z square. But we know that modulus z square can be written as modulus z the whole square. Modulus z value is 1. So we make it 1 square which is equal to 1. Then modulus z2 is equal to modulus 3. 3 means complex number is imaginary part is not there. 3 square plus 0 square. So again we make it, the answer is 3. Root 3 square is 3. Now I am going to check here, the symbol is minus. So I will be using that second property, modulus of modulus z1 minus modulus z2, which is less than or equal to modulus z1 minus z2, which will be less than or equal to z1 plus modulus z1 plus modulus z2. See, both are same, but only the symbol is changed. Now if we substitute, this is modulus 1 minus modulus z2, 3 is less than or equal to modulus z square minus 3, which will be less than or equal to 1 plus 3. See, modulus of minus 2 less than or equal to modulus z square minus 3 less than or equal to 4. Now we know that modulus of minus 2 is 2 less than or equal to modulus z square minus 3, which will be less than or equal to 4. Similarly, we have one more problem that you have to do it as homework. See, problem number 6, if modulus z equal to 2, show that. This you have to do it as homework. Okay. Now we can do the next example problem. Example 2.14, show that the points 1, minus 1 by 2 plus I into root 3 by 2 and minus 1 by 2 minus I into root 3 by 2 are the vertices of an equilateral triangle. So equilateral triangles means we know all the three sides are equal. Three vertices are given, so we can take let Z1, Z2 and Z3. So we have to find out the distance between the two vertices. So all the sides, all the three sides we have to find it out. If all the three sides are equal, then we will say that the given points form a equilateral triangle. So distance between 2 points is modulus Z1 minus Z2 is 8. So when I find it out, Z1, 1 minus 1 by 2 plus I into root 3 by 2. That is modulus 1, if the minus inside, plus 1 by 2, that is minus I into root 3 by 2. So if we separate this, 1 plus 1 by 2, that is 3 by 2 minus I into root 3 by 2. Now we have got real part and imaginary part. So when we find out the modulus, we may get root of real part to the whole square plus imaginary part to the whole square. Here real part is 3 by 2 and the imaginary part is minus root 3 by 2. That is root of 3 square, 9 by 4 plus minus root 3 the whole square is plus 3 by 4. So here inside the root, if we take LCM is 4, 9 plus 3, 12. Isn't it? Now 1 4 is 4, 3 4s are 12. So we have got the answer is root 3. So Z1 minus Z2 we have found out. Now we are going to find out modulus Z2 minus Z3. Z2 minus 1 by 2 plus I into root 3 by 2 minus Z3, that is minus 1 by 2 minus I into root 3 by 2. Shall we separate it? See, minus 1 by 2 plus I into root 3 by 2. This minus into minus plus 1 by 2 minus into minus plus I into root 3 by 2. See here, minus 1 by 2 and plus 1 by 2 will get cancelled. I root 3 by 2 plus I into root 3 by 2. That is 2I into root 3 by 2. 2 and 2 will be getting cancelled. Now that is modulus I into root 3. Shall we find out the value? That is square root of real part is not there, 0 plus imaginary part is root 3 the whole square. So root and square will be removed. Our answer is root 3. Is that clear? Then one more side we have to find it out. That is Z3 minus Z1. Z3 minus 1 by 2 minus I into root 3 by 2 minus Z1 is 1. Now minus 1 by 2 minus 1 we may get, that is minus 3 by 2 minus I into root 3 by 2. Now if the real part and imaginary part is there, we can find it out the modulus value, that is root of real part minus 3 by 2 the whole square plus imaginary part minus root 3 by 2 the whole square. So that is root of minus 3 the whole square is 9 and 2 square is 4 plus minus root 3 the whole square is 3 and 2 square is 4. Now take LCM is 4, 9 plus 3 that is 12. We can divide, isn't it? So root 3. See, all the three values are root 3. So we can write it, since the sides are equal, the given points or the given vertices forms an equilateral triangle. Do you understand this? In the same way, there can be a question forms isosceles triangle. Isosceles triangle means any two sides are equal. If any two sides are equal, we can say the given is isosceles triangle. Okay. This is an important 5-mark question. Example 2.5. Z1, Z2, Z3 be complex numbers such that modulus Z1, modulus Z2 and modulus Z3 is equal to R, which is greater than 0, and Z1 plus Z2 plus Z3 not equal to 0. Prove that. This we have to prove it. Okay, why they have given not equal to 0 more? Because it's given in the denominator. If it is equal to 0, this is totally not defined or infinity. So from the given condition, the given is given modulus Z1 equal to modulus Z2 is equal to modulus Z3 is equal to R. Shall we separate it? See, modulus Z1 equal to R. So that implies modulus Z1 take square, it will become R square. So modulus Z can be written as Z into Z bar. So Z1 into Z1 bar is equal to R square. From this I am going to find it out what is Z1. We may get R square by Z1 bar. Similarly, we have to find out the value of these two. See, modulus Z2 is equal to R. So, which will be implies modulus Z2 the whole square is equal to R square. This can be written as Z2 into Z2 bar is equal to R square. So, I may get Z2 is equal to R square by Z2 bar. Similarly, Z3 will be equal to R square by Z3 bar. Isn't it? Now, just I am going to add this 3. Okay, that is Z1 plus Z2 plus Z3 is equal to R square by Z1 bar plus R square by Z2 bar plus R square by Z3 bar. R square is common, we can take it out. Now for the remaining 3, when we take the LCM, Z1 bar into Z2 bar into Z3 bar, isn't it? Here Z1 bar is there, remaining 2 is missing. So we may get Z2 bar into Z3 bar. Here Z2 bar is there, remaining 2 is not there. That is Z1 bar into Z3 bar. The same way here Z3 is there. So Z1 bar into Z2 bar. Is that clear? Okay, now take the modulus. Modulus Z1 plus Z2 plus Z3 is equal to modulus R square and numerator modulus Z2 bar Z3 bar plus Z1 bar Z3 bar plus Z1 bar Z2 bar divided by modulus Z1 bar Z2 bar and into Z3 bar. So modulus R square is R square, isn't it? See, this I am going to put it as together bar. Z2, Z3 plus Z1, Z3 plus Z1, Z2 the whole bar divided by here also modulus Z1, Z2, Z3 the whole bar. Now we have the condition that modulus Z is always equal to modulus Z bar. So this bar can be removed. So we may get, as per the condition modulus Z equal to modulus Z bar, we have removed the bar. Now you see R square into modulus Z2, Z3 plus Z1, Z3 plus Z1, Z2 divided by, this can be separated, isn't it? See here, this modulus can be separated, isn't it? Modulus Z1 into modulus Z2 into modulus Z3. See, in the condition they have given modulus Z1 equal to modulus Z2 equal to modulus Z3 is equal to R. So, R into R into R. See, 2R will be getting cancelled. Now, The left hand side actually we have modulus Z1 plus Z2 plus Z3, which is equal to modulus Z2 Z3 plus Z1 Z3 plus Z1 Z2 divided by R. Just cross multiply, we may get R is equal to modulus Z2 Z3 plus Z1 Z3 plus Z1 Z2 divided by modulus Z1 plus Z2 plus Z3. Now I can put the modulus together. That is modulus of Z1 Z2 plus Z2 Z3 plus Z3 Z1 by Z1 plus Z2 plus Z3 is equal to R. This is what they have asked us to prove. Simple, but few steps are there to prove. Similar way we have the exam exercise problem also, that also we can do it. Now exercise 2.5, problem number 7. If Z1, Z2, Z3 are three complex numbers such that modulus Z1 equal to 1, modulus Z2 equal to 2 and modulus Z3 equal to 3 and modulus of Z1 plus Z2 plus Z3 equal to 1, show that. This we have to prove. See, same way we can take first these conditions. Okay. The same procedure what we did in the example problem we are going to do. See, square it. Modulus Z1 square is equal to 1. This can be written as Z1 into Z1 bar. Now find it out Z1. That is 1 by Z1 bar. Here modulus Z2 the whole square equal to 2 square 4. Z2 into Z2 bar is equal to 4, or Z2 is equal to 4 by Z2 bar. Similarly, this is modulus Z3 the whole square equal to 3 square 9. Now Z3 into Z3 bar is equal to 9. From this Z3 is equal to 9 by Z3 bar. Is that clear? Same like I am going to find it out. What is Z1 plus Z2 plus Z3? We may get 1 by Z1 bar plus 4 by Z2 bar plus 9 by Z3 bar. Shall we take the LCM? When we take LCM, Z1 bar into Z2 bar into Z3 bar. So here Z1 bar is there. So we may get Z2 bar into Z3 bar plus 4 Z2 bar is there. So Z1 bar into Z3 bar. And here we have Z3 bar. The numerator 9. So 9 into Z1 bar into Z2 bar. Is that clear? Now take that modulus. So modulus Z1 plus Z2 plus Z3 is equal to modulus Z2 bar Z3 bar plus 4 into Z1 bar Z3 bar plus 9 into Z1 bar Z2 bar divided by modulus Z1 bar Z2 bar and into Z3 bar. And this they gave the value is equal to 1. So I am substituting 1 is equal to, and this is modulus Z2 Z3 plus 4 into Z1 Z3 plus 9 into Z1 Z2 the whole bar. Same way the denominator also modulus Z1 Z2 Z3 the whole bar. Okay. Now as per the condition, modulus Z is equal to modulus Z bar. We can write it 1 equal to modulus Z2 Z3 plus 4 into Z1 Z3 plus 9 into Z1 Z2 is divided by, this is modulus Z1 into modulus Z2 into modulus Z3. Now I hope we can substitute the values of modulus Z1, Z2 and Z3. So 1 equal to modulus 9 Z1 Z2 plus 4 Z1 Z3 plus Z2 Z3. As per the answer I have rearranged. Okay. Denominator 1 into 2 into Z3 they gave the value is equal to 3. So 1 into 2 into 3, that is 6. Cross multiply, we may get 6 equal to modulus 9 into Z1 Z2 plus 4 into Z1 Z3 plus Z2 Z3. See, check it. This is what they have asked us to prove. Okay, so today you have only one problem. Study these portions. Do the homework also. See you in the next class. Thank you. Bye-bye.